Right, you ready? Thank you very much. We already have quite a lot of participants in the meeting, and we are also streaming on YouTube at the same time. Thank you very much for coming. This is our fourth month of the IUCAA Weekly Colloquium, and I'm glad to see in the middle of all these seminars going on everywhere on the web, the people have actually continued to come to our weekly colloquium. And as you know, every month or every now and then, we showcase the work of one of our faculty members, and this time it's Debarati's chance. And so I'm very, very happy to welcome Debarati Chatterjee, who is one of our members of faculty and associate professor here at IUCAA, and has been here for a few months already. And she came from Caen in France, and of course after that she was in Frankfurt at the Goethe University for a little while. Her original credentials are doctorate from SINP in Kolkata, the Saha Institute, about 2009. After which she was a Humboldt Fellow, a very distinguished position at the University of Heidelberg. And then she spent some time in Frankfurt working as a guest researcher at FAIR, was in Meudon in Paris for a while, and in Caen. And then continues her various associations with the Humboldt Fellowship. And she works, as you can see, on the interface between nuclear physics and astrophysics. And also, of course, it's become very, very topical in the context of the gravitational wave detections of emerging neutron stars. So I leave you to Debarati, and we leave the questions till the end. If, as you remember, people, for the regulars, we do questions at the end when you can raise your hand. And we'll come back to it. If there's a pressing issue, you can interrupt the speaker, but we'd rather leave all the questions till the end. Over to you, Debarati.
Thank you very much for the introduction and for giving me a chance to give a colloquium. It's my pleasure to be here as a part of IUCAA, one of the premier institutions of astrophysics in India. So I'm just getting started off here in IUCAA, and so I will present today some work that I have been doing in the past few months with a student, Sukrit Jaiswal from IISER in Pune. And I have to say he has done an excellent job. The entire work was discussed online, and he has worked from a distance. So as an undergraduate student, this is not easy. So I would appreciate a lot his efforts. And so this piece of work is up on the archive since a week now. And so let's get started. Let me explain what we have done. So the basic idea, like I was just introduced, so basically I work on the interface of nuclear physics and neutron stars. And so neutron stars, interestingly, are one of the compact stellar objects which are visible throughout the electromagnetic spectrum. So basically from gamma rays, X-rays, through to microwave and radio frequencies. And thanks to the vast advancement of technologies, we have now at our disposal ground-based and space-based telescopes to observe these objects at multiple wavelengths, as you can see in the figure on the right. So these different multi-frequency observations give us a lot of information about phenomena associated with neutron stars. So for example, we know that neutron stars rotate with very periodic spin frequencies, which can be measured. Binary neutron stars give us information about their masses. Precision gives us information about moment of inertia, which is basically a product of mass times radius squared. The recently launched NICER mission is giving us better and better information about neutron star radii. And soon it will give us accuracies up to 5% in radii measurements. So if we have simultaneous measurements of, say, mass and moment of inertia, we can also put constraints on the radius and compare with the nicer measurements. We also have information about temperature from hotspots in neutron stars. Spectra give us information. So for example, X-ray spectra give us information about the compactness or the mass to radius ratio inferred from the gravitational redshift. There are also phenomena like flares and outbursts in neutron stars, which tell us about its strong magnetic field. So the information that we have accumulated about neutron stars can be summarized in a fact sheet like this. So basically, neutron stars are the stellar remnants which are left behind at the evolution of massive stars that end in type 2 supernova explosions. They have masses around, so 1 to 2 solar masses. Radii is of the order of 10 kilometers. So large masses of solar, of the order of solar masses confined within a small radius of only 10 kilometers means that they have extremely high central densities. So it could go as high as 2 to 10 times saturation nuclear density. The temperatures are very low compared to the particle energies, and the magnetic fields are extremely high. So neutron stars are basically astrophysical laboratories to test extreme phenomena or extreme types of matter. So it is a very difficult task to model the neutron star interior. And we have to resort to theoretical modeling for this. So from the surface towards the interior, as the densities increase, neutron stars encounter different kinds of matter. So from iron nuclei at the surface, as we go towards the interior, the densities increase, and we find nuclei which are richer and richer in neutrons. So this region, which is called the outer crust, comprises mainly of nuclei embedded in a sea of electrons. Beyond a certain density called the neutron drift density, neutrons start to escape from the nuclei, and we have a continuum of neutron states. So basically nuclei with a background of electrons and neutrons. As densities further increase, these nuclei start to get squeezed and deformed, having various kinds of different shapes until finally they melt into a uniform liquid of free neutrons, protons, and electrons, and this is called the outer core. When the density of the neutron star interior goes to even higher densities, so it exceeds that of 5 to 10 times saturation density, the matter composition is still very unknown. There are different models to speculate what kind of matter could appear at such high densities. And it is thought that strangeness containing matter, which is actually seen in heavy ion collisions for fractions of a second, could become stable components of these exotic objects. So this is still a matter of speculation, and this is where gravitational waves can play a very big role. So there are observations of relativistic binaries of neutron stars, which allow us to measure, in addition to the regular Keplerian parameters, the post-Keplerian parameters. And from these, we can actually infer very accurately the masses of the neutron stars in the binary. And this has allowed us to make a kind of chart of neutron star masses. And you can see that although most of them earlier neutron stars were believed to cluster around a canonical value of 1.4 solar mass, the new measurements have started to indicate very massive neutron stars. So like these circled masses are above 2 solar masses. So this actually imposes very strong constraints on the neutron star composition. And how is that? Because we can actually, through numerical modeling or through theoretical modeling, we can associate the interior composition of the neutron star with the external structure of the neutron star. So basically, one important ingredient to quantify this is called the equation of state. So the equation of state is actually the relation between the energy density and the pressure for a low temperature system. And there are equations called Tolman-Oppenheimer-Volkoff equations, or TOV equations as they are popularly called. These are equations of relativistic hydrostatic equilibrium, which in simple word means that uh, it's a balance of gravitational pressure acting towards the center, trying to collapse the star, versus the pressure of the participating particles like electrons or neutrons, which support the star against gravitational collapse. So this balance gives what is the equilibrium structure of the neutron star. So if we actually implement the equation of state into these equations, what we obtained is the external structure of the neutron star. So this gives us the mass versus the central density, or mass versus the radius of the neutron star. So typically, this black line you can see for equation of state for nucleons and leptons only. So for nucleon, if there are only neutrons, protons, electrons, then it would be a very stiff or a steep equation of state curve. And if you see the corresponding map on the mass density relation, you see that the mass is actually high. Whereas if you have some exotic components in the interior, this would mean the system loses some pressure, and the equation of state is softer, and correspondingly the maximum masses are lower. So this means that this idea can be used to impose constraints on the equation of state of neutron stars by measuring their maximum masses. So this red line on the mass radius curve gives us a cutoff above which the neutron star models satisfy this constraint, which means that they theoretically allow for explanation of this maximum mass, whereas the ones which lie below do not. Um, this is very interesting because this allows us to probe very high densities, so matter, so extremely dense kind of matter. So if you see this density temperature curve, which is also called the phase diagram, so this map of density versus temperature, so there are various different terrestrial experiments and astrophysical phenomena which lie on different parts of this diagram. So neutron stars correspond to the low density, the high density, low temperature part of the curve. There are experiments like heavy-ion collisions. You must have heard about CERN or LHC. So these kind of heavy-ion collision experiments, they probe hot matter, and nuclear experiments probe low temperature, low density matter. So these give us complementary information about the equation of state. And so this is something very useful for us for theoretical modeling, because there are experiments like electric dipole polarizability, giant and pygmy dipole resonances, neutron skin thickness measurements, and so on. So these are typical nuclear experiments. These actually give us information about the nuclear equation of state, which is useful for modeling neutron star matter. So we'll see how this works out. So basically, when we are talking about neutron star matter, we are going from nuclear experiments higher in density. And not only that, we are going higher in neutron-proton asymmetry. And this is because nuclear experiments probe neutron-proton ratios which are close to 1, whereas neutron stars are primarily composed of neutrons. So the neutron ratio is much higher than the proton ratio. So this means that on two different aspects, neutron stars differ from nuclear experiments, and this must be taken into account during theoretical modeling. So when we account for this, this is done in the following way. So, for example, the energy per particle of a system can be expanded as a Taylor series expansion with respect to a parameter x, which is basically telling you how far you are going from the saturation density. And on the other hand, this is written in two components. One, the IS is the isoscalar component, which means these parameters do not, the coefficients of the expansion do not depend on the neutron-proton asymmetry. On the other hand, there is another segment which depends on the neutron-proton asymmetry. So basically, this energy per particle of nuclei or neutron matter. So this can be written as an isoscalar part, isoscalar expansion, and an isovector expansion. And these coefficients can be determined from these experimentally determined empirical observables that we talked about. So the basic idea is this, that you have a large number of models which have these coefficients, which account for these coefficients in their parameter set. So let's look at it this way. So basically, there are some parameters in this expansion which are known very accurately. So, for example, the saturation density and the energy at saturation, these are experimentally determined very accurately. But as you go higher and higher in the expansion, so the following terms are explored inside a small interval, whereas when you go to even higher terms in the expansion, so like the second order, third order terms in the expansion, they cannot be determined very well from nuclear experiments, which mean they have very large uncertainties. So this is the reason why there is a large proliferation of theoretical models because of this uncertainty. As you go away from the saturation density where nuclear experiments are performed, you know less and less about these higher order quantities. So how can we then construct a theoretical model? So there are different ways of doing it, and so there are two main classes. So one is the microscopic models. So what these models do is they start from this vacuum realistic neutron-neutron interactions, which are which are derived from nuclear experiments, and then they go away from the vacuum quantities. And on the other hand, there are these phenomenological models where there are certain coupling parameters, and these coupling parameters are tuned around the saturation point so that these couplings explain the observed nuclear experimental phenomena. So when you see these large number of models, so basically in this figure, this is a compilation of these different theoretical models, and this only shows you that although all of these different models satisfy certain nuclear experimental quantities, they are unable to explain some other. And there is no one model, one equation of state that can explain all the different nuclear experimental quantities and explain neutron star phenomena. So this is the reason why we have these different models which do not agree. And this gives rise to some problems which are related to the uncertainty in the determination of these nuclear experimental quantities. So, for example, here we have again some plots showing you the correlations between these different nuclear observables for these different models, and as you can see, some of these fall on the predicted lines and some of them don't agree at all. So it is not clear whether the difference in these different models, so the mean field models and the non-relativistic curve models, all these different models, the difference could arise from the underlying physics, or it could be that these correlations are spurious. So this is not clear. And this is something which is being worked upon right now. So different nuclear theoretical models are trying to achieve better and better correlations among the different nuclear experimental observables and the couplings of the model. This is where gravitational waves come in, because all these astrophysical observables or astrophysical phenomena associated with neutron stars that you see in multi-wavelength frequencies, these are all model dependent. So you cannot actually observe inside the neutron star, because these are basically linked to the surface. Whereas gravitational waves for the first time actually allow us to look into the neutron star interior and try to observe what's actually happening there. So the good news is that gravitational waves, which were predicted as long ago as back in 1970s, when Halsey and Taylor observed the first pulsar, which was slowing down, and so they predicted that this is actually a binary system of neutron stars, which is approaching each other more and more, because they are losing energy because of emission of gravitational waves. So this was predicted back in 1970s, and as you can see from this figure, they had actually predicted this phenomena, and which was extremely compatible with general relativistic prediction and observations. So they were awarded the Nobel Prize in 1993. And so many years later, first time in 2014, and then in 2017, we had the first observation of gravitational waves, and gravitational waves particularly from binary neutron stars. So this is great news. So something that was speculated for so long has become reality, and we can now actually look into the interior of neutron stars with the help of gravitational waves. And what was even more spectacular is that this system, the GW170817, which was observed in 2017, was in conjunction with multi-wavelength observations, which gave us a really very rich spectrum of information about these objects. So, so what is very interesting about neutron star mergers is that when the neutron stars in binary, they approach each other, uh, they they are tidally coupled because of the strong gravitational fields, and because of this, they deform each other. And this tidal deformation actually depends on the underlying equation of state. So this tidal deformability has been extremely useful in the past few years. There have been many papers in the literature which have tried to connect the underlying equation of state and the tidal deformability in neutron star mergers. Further, what has not yet been explored but is expected to be explored very soon in the near future are quasi-normal mode oscillations in neutron stars. So these could be isolated or in binary. So what is this? So this arises from any kind of time-varying quadrupolar deformation in the neutron star, and depending on the restoring force, which brings the system back from the perturbed state to the equilibrium state, is so they are classified according to that restoring force. So for example, for the non-axis symmetric oscillations, if so F modes are associated with the fundamental non-radial oscillations, P modes with the pressure modes, G modes are due to buoyancy, R modes are rotational modes, so they are restored by the Coriolis force. And so these F, P, G, and R modes are very similar to fluid modes. So these are also seen in other, so stellar oscillations or solar oscillations. What is very peculiar about neutron stars are the axial W modes. And these are pure space-time modes, which appear because neutron stars are extremely relativistic objects. Not only that, neutron stars can also emit gravitational waves if there are any deformations on the surface, which are also called mountains, even if they are a few centimeters high, because they are crushed to such small heights because of the strong gravity. Neutron stars also have extremely strong magnetic fields, which also deform the neutron star, and any deformation which is time varying will also emit gravitational waves. So all these different deformations in neutron stars can be sources of gravitational waves, which we will be able to observe with the gravitational wave detectors. What is interesting is that all these deformations are actually they contain signatures of the underlying composition of the neutron star. So the mountains depend on what would be the elasticity of the crust. The different quasi-normal modes of oscillation, they give us information about the crust, the core, or even the crust-core interface, and the underlying equations or state of the crust and the core. So basically, gravitational waves are bringing us, they are like messengers which bring us information from the core of the neutron star, and embedded in the form of frequency and time scale that we observe with the gravitational wave detectors. What has recently opened up an extremely exciting opportunity is that these oscillation modes, which were thought to appear only in isolated modes, they are also, there is a possibility that these are also excited during binary coalescence of neutron stars. So this is something that we have already measured and we already have the data. But the problem is the interpretation of this is extremely difficult. The reason is that not only are these post-merger gravitational waves difficult to decipher, but also that these modes may be coupled with each other. So, for example, F modes, which are thought to be one of the most dominant gravitational wave sources, these are thought to be related to tidal deformability. The G modes, which are the buoyant modes from hot neutron star merger remnant, they may impact the gravitational wave emission. And so there could be resonances between the G modes and tides, which may also affect the gravitational wave signal. There could also be higher order mode coupling. For example, the P modes could be coupled to the G modes, and also there is a concern about the saturation of these different modes. So if these modes are coupled, this could control how much energy is going into one mode and which mode will get saturated first. So this is a very complicated dynamics. And this is a field which is just starting to be explored, which is great news. But the problem is that we do not have enough theoretical models to confront this problem. But this has opened up an entirely new field of astrophysics called asteroseismology, particularly gravitational wave asteroseismology. And the efforts have started back in the 1990s. And before I go into my own work, I will review a little bit about what has already been done and what facts we have already accumulated over the past few years. So a major part of the work concerning astroseismology was started in the 1990s, particularly by Niels Andersen from Southampton and Kostas Kokotas from Tübingen. And so they found some very interesting correlations between the frequency and time scales of some of these oscillation modes and with parameters related to the neutron star. So they speculated that spectral information tells us that the F mode oscillation frequency has a correlation with the average density. Well, this is not surprising because any kind of dynamical phenomena, it is expected that the frequency has a kind of correlation with the average density. So what they did was they took a number of different polytropic models. Polytropic equation of state is one where the pressure is related to a power law of the density. So it is a simple model which does not take into account the underlying composition of the neutron star. With varying polytropic indices, so different polytropes, what they did was they tried to find a correlation of the frequency of the F mode with a square root of the average density. And they proposed a certain relation, fit relation. And on the other side, for W modes, they also predicted that the time scale of W modes had a correlation with compactness or with the mass to radius ratio. And what they proposed in their work was that if gravitational waves can measure simultaneously F mode frequencies and W mode frequency, then we could very easily, using these fit formulas, derive the mass and radius ratio and therefore constrain the equation of state of a neutron star. So this is called the inverse problem of astroseismology, which means that we observe the frequency and time scale from gravitational wave observations, and we determine the interior composition from it. So this was a remarkable speculation. They further improved upon this in 1998 by taking a number of realistic neutron star models. So you can see here, they took into account large number of neutron star models, and this is the corresponding mass radius diagram. But as you can see here, the 2 solar mass limit now rules out many of the models they had considered in this work. So this is something that has to be upgraded. With this observation, they calculated the same thing. So they calculated the F mode frequency and its correlation with the square root of the average density, and they tried to improve this astroseismology empirical relation that can be used to determine the mass and radius. Further, there was work done in 2005 by the group of Ferrari Gualtieri in Rome, and what they did was not only consider realistic neutron star models, they also included, in addition to the pure nucleonic stars, they included neutron stars which contained exotic forms of matter in the core, like hyperons and so on. And so you can see again another correlation plot of the F mode frequencies with the square root of the average density. And on this figure, the different colored lines show the different equations of state considered. The AK fit, the black bold line for the AK fit, means that the previous fit from Anderson and Cockatus. And the new fit, the dashed line, shows you that in their work, they proposed that Anderson Cockatus had overestimated the frequency, and they proposed another correction to this by taking into account this spectrum of realistic equations of state. So you see, I think you already see the problem. The problem is that every time you consider different equations of state, you include some more information, and then the fit relation changes, and correspondingly the mass radius values that will be determined from the frequency will change, and the interpretation of the equation of state will change. So this is kind of like a circular problem. A lot of recent work was done by in the group of Cockatus and Tübingen. With Geertych, what he did recently was introducing rotation in the neutron stars and calculating the F modes. He showed that the F modes would actually split. So all these L is the spectral number. So the L equal to M equal to 2 modes for quadrupoles would actually split into 2L plus 1 modes because of rotation. And so the degeneracy would be broken due to rotation. And on the left-hand figure, so this is for inertial frame frequencies versus rotation frequency, and the same figure for the core rotating frame. And so I mean, what is interesting is that from this work, he again derived the non-rotating limit. And comparing with the previous works from Anderson and Cockatus, so in this figure you can see this straight line with square boxes, unfilled boxes. So these are the values derived by Anderson Cockatus in 98. And the black filled boxes are the new fit, which was obtained in this work. And again, you see that this time Anderson Cockatus seem to be underestimating the values of frequency. So they suggested another fit relation to be used in astroseismology. But again, here the equations of state considered were polytropes, which means they do not have any underlying nuclear physics. This work was further improved by Daniela Doneva in the same group, and she also studied rotation, so F modes under rotation, and she included, first of all, higher order modes. And the reason was that at this time there was an observation that higher order modes could actually have a higher chance to be observed by gravitational wave detectors. So I will come to this point soon. So she considered higher order modes, and also she considered realistic equations of state, but again only 5 realistic equations of state which are not representative. So it's a random choice of 5 realistic equations of state. And you can see again that many of these do not satisfy the observed 2 solar mass neutron star limit, which means they are not realistic equations of state. So what they obtained again from the non-rotating limit were frequency, average density correlations for different modes. So L equal to 2 quadruple modes, and also higher order modes, L equal to 3 and L equal to 4. And she derived fit relations for these scattered data points from the different realistic models. You can see that the models actually have a scatter, which means that the frequencies do depend on the underlying equation of state. And she provided these relations, again, alternatively to be used in astroseismology. And as you can see in the bottom left figure, she also plotted the previous results from the full GR Anderson and Cockatus paper, which is the lower line, and that from Gettig and Cockatus. So this means again that this new fit does not comply with the previous ones. So this means that, like I explained, that this is like a a chicken and egg problem. It's like every time you include new equations of state, you get a new fit, which gives you new values of mass and radius, and this will give you a different equation of state. So to complicate things further, recently Salcedo's group, they included exotic forms of matter, so hyperon matter and quark matter and so on. And they showed that even this fit relation would not do, because including exotic forms of matter makes the frequencies very different from that of nucleonic cases. So recently, a paper from Bao-An Lee, who is, what he suggested was that instead of the frequency density correlation, one could actually use a scale correlation between the product of mass and frequency and that of the compactness. So you see that we have different groups making making efforts to improve the empirical relations for astroseismology, but depending on the equations of state, the fit relations are different every time. One must also remember this is not the end of the story. One has to calculate what is called the instability window in order to understand whether we can actually measure these F mode frequencies from the gravitational waves. So the F mode, so any instability window actually means that it's a plot of the frequency of the star versus its temperature. And basically, this is bordered on 2 sides by the different viscosities that appear inside the neutron star. like the bulk viscosity, which appears at high densities, and shear viscosity, or in the case of superfluid neutron stars, there is mutual friction, which appears. So these are different kinds of dissipation in the star. So for example, if you drive a car, I mean, you need friction to come to a stop. It's the same thing. So gravitational waves make the star unstable through a mechanism called CFS, Chandrasekhar-Friedman-Schutz instability. And this makes the star like completely unstable. But the dissipation arising from inside the star would actually balance this. And the region where the two are balanced is called the instability window. And any object which is within the instability window is actually the one which is unstable, which means that if we observe a star within this instability window, it will emit gravitational waves that we can detect. So, Geertig and Kokotas in their paper determined this for the first time. They determined the F mode instability window, and they also showed that you can barely see this blue line. So this L equal to M equal to 2 mode. So the quadrupole mode, which was actually the most considered at that time, considered to be the dominant component, is actually not dominant at all. Whereas the higher order modes like the 3 and 4 were found to be playing a significant role. This was even, I mean, the situation was even more optimistic when Daniela considered realistic equations of state. So you can see the black line from L equal to 2 moles. This was not negligible anymore if you consider realistic equations of state, but they studied this only for 1 or 2 equations of state. In another recent paper in their group, they also studied unstable F modes in neutron star merger remnants, and they showed again inversely that the F modes become unstable for L equal to 2 modes rather than L equal to 3 modes, which means that the quadruple components will be again important in the case of neutron star mergers. So this story is not very easy to handle. So basically, you have all these underlying equations of state that you must be able to model with your knowledge of nuclear physics. Then you have to model the frequency, determine the frequency, and link it through astroseismology with the neutron star parameters. So let's see how we can confront this in a more systematic way. So what we did in our work was we started with a relativistic mean field model, which is basically a phenomenological model. So here we started with typically with a mean field Lagrangian, which means there are interactions between the different particles. So for this work, we considered only neutrons, protons, and electrons, and not exotic components. So for these components, they interact by exchanging some mesons, like sigma, omega, rho mesons, which explain its underlying nucleon-nucleon interaction. And from the calibration of the model is done in this way. All these coupling constants of the nucleon-nucleon interaction are actually fitted to the saturation properties of nuclear experiments, which are determined from nuclear experiments. This I explained in this talk today. And as I told you already earlier, that these saturation properties are actually known only within an uncertainty range. So this means that the uncertainty of these parameters is the uncertainty of our equation of state. So we did a systematic study of what would be the effect of these uncertainties on the F modes. To do this, one has to solve for the oscillation equations. There is an approximation called the Colloquium approximation, which means that we neglect the metric perturbations. So there are perturbations of the fluid as well as perturbations of the background space-time. But actually, it's a very complicated problem to solve. So until now, everybody has been using the Cowling approximation, which means we neglect the background space-time. There have been some efforts to avoid this approximation, and it has been found that the values of frequency vary up to 30% for F modes, and if you go to higher order modes, then this difference is lower. So these pulsation equations have to be solved with subject to certain boundary conditions. So this is basically an eigenvalue problem. Once you solve it, you can obtain the F mode frequency. So what we did was this. So in our relativistic mean field model, we can take different input nuclear saturation parameters. So these nuclear saturation parameters we varied within the uncertainty range, which is known from nuclear physics experiments. First, we did a couple of tests with known relativistic mean field models, which have been very successful in explaining neutron star phenomena and nuclei. So the GM1 and GM3 model, which are from Glendening and Moskowski from 95. So I show you here just the test for this numerical scheme. So we determined from the Lagrangian, from the nucleon interaction, we determined the equation of state. So this is how it looks like. We calculated by solving the hydrostatic equilibrium equations. We found the mass and radius plot, and then we solved the perturbation equations and obtained the frequencies, F mode frequency versus mass plots for the GM1 and GM3 sets. So first, let's compare with the existing literature and see what we have. So we found that our frequencies were very compatible. They were consistent with the existing literature. You can see, for example, here in the paper from Flores Lugones, that this bold black line is corresponds to the GM1, and this is also what we get from our calculations. Similarly for the other papers. So this gave us assurance to go on and calculate the F modes for all the other equations of state. And so now what we did was, our aim was to perform a systematic study of the different equations of state. And so for this, like I said, we varied um, because this is an undergraduate project, and it was a 2-month project, so we did not vary all of them, the parameters simultaneously, because this would be numerically very complicated. So what we did was, each time we took one parameter to vary within the uncertainty range, holding the others fixed. And so this is typically a sensitivity study. So you see the sensitivity of the F mode frequencies to the underlying equation of state. So in these two figures, you see now the values that the equations of state span, and the same for the mass and radius. And you see that now the equations of state we considered are well above the 2 solar mass limit, which means that they are realistic. For the sensitivity study, now we vary the parameters one by one, and so let's see what we get. So if we consider the saturation energy, so the energy per particle at saturation, so it is known to vary within this limit, and if we vary them within this limit, keeping the other parameters fixed, we see that there is almost no change in the F mode frequencies. And the same goes for the incompressibility, which is also a saturation parameter. Similarly, for the symmetry energy and the slope of symmetry energy. So which ones are actually found to play a role in the F mode frequencies, and these were actually the saturation density, so the density at saturation of nuclear matter, and particularly it was the effective nucleon mass. So basically the in medium nucleon mass was found to play the major role in controlling the F mode frequencies. So we decided to see how to interpret information from this, and how this uncertainty in effective nucleon mass actually affects astroseismology relations. To do that, we started with a calculation of the tidal deformability that I talked about. And we calculated the tidal deformability for this range of effective masses and compared with the existing literature. So on the right, this is a figure from the latest paper from the LIGO-Virgo collaboration and another PRL paper. And you see that the R values span exactly the same range as the observations. So this is a reasonable investigation to continue to perform. So now we calculated the frequency of the F modes as a function of the tidal deformability, and you can see that there is this span of frequencies. There is not much work related to this in the literature, but we found one work from Bao Wan Li recently where they plotted a large number of parametrized equations of state obtained by random variations of realistic parameters, and they obtained a similar fit considering tidal deformability between 100 and 700, which they claim that where the minimum and maximum values obtained from gravitational wave observations. So if you actually translate this, so 100 to 800 in our plot is actually very consistent with their calculation as well. Further, we also make some plots of the frequency versus compactness, or the ratio of the mass to the radius, and compared it with the literature. There is also not much existing literature about this, but we found that the values were consistent with the speculations. There is a further, one can also determine the gravitational redshift from, which is another observational quantity from the compactness using this relation. And we also compared this with the existing literature. So we find that gravitational, if the gravitational redshift is measured, we also have additional information about how to constrain the equation of state given its frequency. Finally, we probed the empirical relations that everybody has been trying to fit over and over again, but this time we have a systematic study, which means that we know the maximum span of the F mode frequencies, for the variations of the saturation density and effective mass, we've obtained these fit relations, which are now ready to be used for astroseismology, which means that you can, if you can deduce frequencies from gravitational wave observation, you can use these to obtain the mass radius relation. And lastly, we also compared. We also investigated the alternative astroseismological relation, which is the scaled omega, so the scaled so product of mass and frequency versus compactness. And indeed, we also support that the fact that this relation is robust. So you can see that the variation in the effective mass, which means the variation in the different equations of state, do not affect this universal relation. And if one applies this to the inverse problem, then one can actually obtain a much more model independent value for the mass to radius ratio. Whereas we also probed some other scaled relations which do not seem to show universality. So finally, I come to a recap of the work which was done. So basically, our aim of this work was to investigate the role of the underlying dense matter physics, so nuclear physics, on F mode oscillations in gravitational waves emitted by unstable neutron stars. So what we did was, within the framework of the relativistic mean field model, we performed a systematic investigations of the uncertainties in empirical saturation parameters which are obtained from the state-of-the-art nuclear experimental data, and we saw how these influence the F mode frequencies. All the equations of state we considered are compatible with the 2 solar mass maximum mass limit, which was not so in the previous cases, the older investigations. We found the nuclear in medium mass mass to be the most dominant parameter controlling the F modes. We also investigated the effect of uncertainty, so the experimental uncertainty in this in medium nucleon mass on the different relations between frequencies of F modes and parameters of neutron stars like tidal deformability, compactness, and gravitational redshift, which can be observed from multi-messenger astronomical observations. We studied whether this uncertainty in determination of effective nucleon mass affects the empirical relations that have been suggested for gravitational wave astroseismology. And finally, we also obtained linear fits to the correlations between F mode frequencies and stellar density for the quadrupole and higher order modes of higher order F modes. So this is basically work in progress. I have also a couple of grad students, Vikram and Suprabhu, who are also looking at effects of exotic components like hyperons on these F modes and effect of rotation and magnetic field. And of course, if one wants to confront data from neutron star merger remnants, gravitational waves frequencies from neutron star merger remnants, then one has to account for effects due to rotation or from strong magnetic fields. And also one must consider exotic components of matter like strangeness containing matter, hyperons, kaons, or even deconfined quark matter. Further, one also must continue to calculate the instability window of F modes in order to understand whether there will be unstable neutron stars within that frequency temperature range. There is also much more work to do. So there is a coupling of F modes with R modes, G modes, and so these inter-mode coupling determines what will be the maximum amplitude of these unstable modes. So basically there is a lot of underlying nuclear and theoretical astrophysics which goes into modeling that will be extremely interesting for upcoming projects like LIGO India and so on. And what has been suggested in recent studies is that these unstable modes, there have been calculations which show that they could be detectable by the Einstein telescope for sources in the Virgo cluster, or even by the advanced LIGO Virgo in the optimistic cases. So this opens up a fantastic opportunity to constrain underlying nuclear physics, given information about neutron stars, about multi-messenger neutron star observations, and gravitational wave astrophysics. In the near future, we will also have in addition to advanced LIGO, the Einstein telescope, which will provide us much more information about frequency and time scales of these unstable modes. And I am also associated with the LIGO India project, which is an upcoming project. Hopefully, this will also contribute to information about neutron stars with respect to nuclear physics and multi-messenger astrophysics. So thank you very much for your attention, and I thank all the faculty, the computing section of IUCAA, the LIGO India team at IUCAA, and everyone who has supported me, the unsung heroes of IUCAA, who are, of course, also the canteen and Dr. Savaskar and everyone who have kept me healthy and fit to work over the past few months. Thank you very much.
Thank you very much, Debarati. And it's been a challenge keeping fit during this lockdown period. But thank you very much. So a great talk, and already so many hands are up. So let's start with Shukanto. Shukanto, please unmute yourself. Go ahead, Shukanto, unmute.
Just got unmuted. Thank you, Debarati, for a very nice talk. I'll start, okay, maybe not start. Okay, I have a couple of questions regarding how to use F mode observations to constrain nuclear parameters such as even M star, right? So you, towards the end, mentioned that, for example, the L equal to 2, M equal to 2 neutron star merger, post-merger frequency can be picked up with gravitational wave observations. And so, but then if I tell you that, so there's a work I contributed to a few years ago where we showed that we can measure that frequency with an accuracy of something like 5% in advanced LIGO-like sensitivities. Can you invert that to tell me how whether that makes any effect in constraining the value of M star? You showed some plots, right, of how this frequency it varies for different equations, well, for different values of M star.
Yeah, actually, so as I had just reviewed all these different literature, if you remember. So all the, I mean, there is this spectrum of equations of state which do not agree, and the reason why people have been trying to find one universal astroseismology relation is to find an equation of state independent relation from which we can find the mass radius ratio, and then invert them. So this can be done also by Bayesian analysis or uh, by inversion. And so this work is different because in this work we are not doing the inverse problem. But what we have done is we have done a systematic study from the equation of state and the variation of the nuclear saturation parameters systematically to obtain the frequency. So basically this is not I mean, of course we also derived in the end the linear fits, and this also should give an improved linear fit to be used in astroseismology. But we also are proposing the fact that there is a systematic investigation that can be done also from the nuclear physics side in order to obtain the observed frequencies of F modes, so that by comparison we can try to obtain the underlying nuclear physics data.
Okay. Real quick, the last universality relation you showed, do you understand the fundamental reason behind this? Is it because you're limiting yourself to a specific class of equations of state?
Do you mean this one? Are you talking about this the scaled mass, the scale frequency versus compactness, or can you hear me, Sukanta?
Sukanta, are you still there? I think it's still muted.
I was muted back. I could not unmute myself, so I was just unmuted.
Not me. I didn't do it.
No problem. Yeah, it was indeed that plot you were showing towards. Yeah, this one. Thanks.
Right. Yeah, so this one, you can actually check the paper from Bawan Lee. This is a very recent paper, very interesting paper, because they did almost like a Bayesian analysis. They performed a parameterized equation of state study considering a large number, about I think 4,000 different equations of state, and like a random variation of the parameters, very similar to what I have done, but I have done it in a relativistic mean field model and varied them systematically within the nuclear experimental bounds. And so their suggestion, I think they tried also to propose different correlations, but this one is independent. So I actually tested the different universality relations, and I find this one to be the most robust.
Thank you.
Yeah.
For me.
So Shomak is
you're muted.
Yeah.
Yeah. Next in line, Dipankar. I've unmuted you.
Yeah, very nice talk, Debarati.
Thank you.
Very good work as well.
Thank you.
I had a very quick question. Suppose in the data, you do find an oscillation. Is there an unambiguous way to identify which mode it is so that one can apply these relations, or do you need to find a bunch of frequencies to figure that out?
I mean, most of the works actually suggest multiple frequencies. I mean, F mode, W mode, G mode, and then comparison among them. The reason why, you can actually tell the difference for some of the some of the modes is because they are. I do not have a plot for it. Right? Maybe wait. I think there. Yeah, this one. Yeah. So here you can see that they are actually. Yeah, can you see? So F mode, W mode, P mode, they are actually around a different central value. So basically you can tell which mode is what, you can differentiate between the different modes. And then within that mode, you can, the challenge is to find what is the underlying equation of state. But then of course there is also like interplay between the modes, and we still don't know what would happen if you have hybrid modes and quark matter, and this could also like I showed some plots, this could also vary the F mode. So maybe we have some modes which are away from the central value. So this is something like work in progress and something to explore.
This figure on the right here, does it cover the full possible range of equations of state, or
No. I think nobody has. I mean, most of the people there have this is what I was trying to review, like in the beginning, that different people justify their choice of equations of state. Like the last one I said from Bawan Lee, this takes 4,000 equations of state. But the thing is, again, maybe like we have this. If we have a 2.4 solar mass neutron star, this will again create other constraints. So basically, I think the only solution would be to do a systematic study where you can justify from, even if you have updated nuclear experimental data, you can actually update, you can actually easily from your figures interpret what would be the consequences, instead of just taking some random choices of realistic or parametric models and trying to find EOS independent result from that.
Yeah, fair enough. Thank you.
Thanks very much. I was just checking the YouTube feed where there are about 15-20 people, but they don't seem to have any questions. Dipanjan, of course, has come up with something. So Dipanjan, go ahead.
Hi. So actually, my first question was asked by Dipankar, and so but question related to that. So in the last part of your conclusion slide, you mentioned about the mode coupling, and this is again related to the different modes joining together. So what are the difficulties from the observational side? You said that mode coupling would affect the amplitude. And if this sort of dilutes the constraints, does it also dilutes the constraint on the m/r on the compactness ratios?
Well, I mean, if like I said in the inverse problem, I mean, we are taking the F mode frequency or the astroseismology relation, and from that we are trying to derive the m/r. So if the frequency is wrong, then of course, I mean, all our interpretation is wrong. The problem is that if you have multiple modes, what is said is that there would be, say, for example, a parent mode, it channels its energy into these daughter modes, and then it saturates, which means that there was an unstable mode, but the energy goes into some other modes, and therefore this leads to saturation of this mode. And this involves a complex evolution of the problem. So evolution means there is a interplay between frequency, temperature, magnetic field, which determines how this F modes will evolve. And there is something called suprathermal effect. So suprathermal effect means that okay, let's not explain this right now, but I mean, this can also play a role in saturating the mode. So this mode saturation is a complicated problem that is still under investigation, and this coupling of modes makes it even more complicated, because it's like energy being channeled from one mode to the other, and we don't know yet what the dynamics is like.
I see. I had one other quick question, if Shomak allows.
Yes, of course, go ahead.
Yeah, so when you had listed the sources of gravitational waves, you talked about the different F mode, W, but in the top you had these mountains and others which we did not elaborate much about. So my question is on that. So especially when in a merger system, the system is very messy, and you can also have fallback material that can fall back onto the remnant compact object if it's a remnant, say, short-lived magnetar or something like that, which is giving out some sort of a emission. So have people in the community modeled this kind of things, where you also have a hyperaccretion, which will also give you some sort of local mountain formations that will also add to the oscillations, which will add to the gravitational wave signal and compound the difficulties with identifying the different modes. So I'm talking about.
Are you talking about binary mergers?
I'm talking about binary mergers, yes.
So I think For binary mergers, the situation is taken to be pretty simple, and just that there are two neutron stars which deform each other tidally and then coalesce. Of course, there are complicated hydrodynamical simulations which take this into account. They take a lot of things into account. Yeah. So, but I mean, combining this with mountains is complicated because actually these are different frequency ranges as well. So all these different gravitational wave sources that I talked about, they emit, they are different time varying components, and they give rise to different frequencies. So if you actually look at the gravitational wave spectrum, the problem is that some of these might be combined them from the gravitational wave signal, and also sometimes they are very distinct in their frequency range. So
if I may quickly, that signal will be very weak compared to the quadrupolar dominant mode.
Yeah,
I see. Okay, thanks.
Okay, so Kandu next.
Debarati, nice talk. I was particularly interested in the equations, which went by pretty fast. Now, somewhere you wrote down a Lagrangian, and somewhere you wrote down a perturbation equation for some metric. So I didn't know where the Lagrangian came into the equation, where the different modes came into those equations.
right. So to construct an equation of state in the relativistic mean field model, what you do is actually you start with the nucleon-nucleon interaction. And this Lagrangian actually accounts for this nucleon-nucleon interaction. From this Lagrangian, you actually have to solve the coupled, you assume a mean field. So there is a background field of the nucleons, and so you calculate the energy and pressure with this mean field approximation. This energy and pressure gives you the, I did not go into the details. Yeah, energy and pressure.
Problem. I just wanted to get a flavor. So
yeah, energy and pressure gives you the equation of state. Then you solve this, the energy and density pressure goes into this kind of relation, or also in the hydrodynamic TOV equations, which gives you the external structure or this mode oscillations.
So where do the different modes go in this equation? The F mode, the...
Yeah, so this is actually an eigenvalue equation. So the F mode is the fundamental mode. So basically it's if you solve this as a real, if in the Cowling approximation, you get only real frequencies, and this is, if you just take the most fundamental frequency, it will be the F mode. But for higher order modes like P modes and so on, you have to solve this coupled eigenvalue problem to get the higher modes.
Yeah, I should also just point out that Nishant has done a lot of stuff on these different modes in the solar seismology.
Yes.
Yeah, so he's locally there. So you both should talk on this.
Yeah. We had a little bit of discussion on this, but I really want to find out more from his expertise.
Nice. Thank you.
Great, thanks. Indulekha has her hand up. Unmute. Go ahead, Indulekha.
Yeah, this is just a naive question. I suppose these modes might be getting excited during pulsar glitches, and whether we could find out anything from about their decay rates or relative amplitudes, etc. from there?
Yes, definitely. So glitches are something which are among the gravitational wave sources in neutron stars. Until now, gravitational waves have not been detected from glitches. So every time they are not detected, it puts an upper limit on the gravitational waves that you can expect from glitches. But yeah, glitches are also one phenomena which since it is a deformation which is time varying, so this definitely will also emit gravitational waves.
Thank you.
Great, thank you. Thanks. Are there any more questions? We're all waiting for the NASA Mars Perseverance launch, which is actually 5 minutes left for the launch. So we'll applaud Debarati, and people are welcome to use the reactions to applaud in Zoom. Thank you very much. It was an excellent talk and great questions. So we'll